Okay, so the last topic of function analysis is concavity and points of inflection. So when you look at the curves, we've got two different types. We've got this one that looks like an up parabola and then a down parabola. So we refer to curvature as concavity, okay? So there's two types. One is concave up. So you think of it holds water. If you draw tangent lines at the points shown, and I know I'm off, then what you'll notice is all the tangent lines are under the curve, okay? So that's going to come up later. But also it says, what is true about the slopes of the lines as you go from left to right? So as we go, the slopes go from negative to positive, okay? And that's the tangent slopes. Also, we'll notice that they get bigger, okay? So also get steeper, because we could start at like -2. This would be like -1/2, 0, 1/2, 3. And so even as we go left to right, they do go from negative to positive, and the slopes themselves, the values get steeper. So let's look at concave down. So concave down is kind of like a hill, or you would say it spills water. And if we look at the tangent lines, what you're going to notice is that first, all the tangent lines are above the graph. Like I said, that's a terrible one. That idea is going to come later as well. But our slopes go from positive to negative, which refers to increasing and decreasing. But the actual values itself, so let's say that was 3, this one's less steep, even less steep, and we keep getting smaller. So our slope values get smaller. Okay? So that's what leads to the idea of concavity. It's the rate of growth of the slopes, okay? So concavity, we're going to define it using all of this notation. So if these were justifications, you could use this notation. So a curve always has to be differentiable on the interval. It's always going to be an open interval. The graph is concave up if your derivative is increasing, okay? So that's what we would say if something was concave up. So, and we abbreviate it concave, we'll say up. Concave down means that your slope or your derivative is decreasing. So concave down. We interpret f prime increasing as f double prime is greater than 0. Does that make sense? So if you want to know if something is increasing, you do its derivative. So that's why it's referring to the second derivative. Does that make sense? Okay, that's kind of a connection that I think gets lost. If you want to know if the y values are increasing, you do the first derivative, because the original is the y values. If you want to know increasing, it says take the derivative. So if you want to know if your slopes are increasing or decreasing, you take the derivative of the slope. Well, slope is the first, so increasing, decreasing would use the second derivative signs, okay? So this is just it, all in notation. If your second derivative equals 0, it means that you don't have any concavity at that point. So it would have to be a straight line. Diagonal, horizontal, it doesn't matter. By definition, an inflection point, we saw the word critical point, but an inflection point is where the graph changes concavity. So we're going to know that our second derivative has to equal 0, but it also needs to change signs. We don't call this a critical point though, okay? We can call this a possible important point, possible critical, I don't even want to say critical point, but it's just called an inflection point. So if we want to determine inflection points, basically we're going to do the same thing. You're going to set up a sign chart, just like we did with the first derivative, but you want to label it for the second derivative. And typically, wherever your critical points were, that is not where your possible points of inflection are, okay? And you would just put whatever your possible point of inflection was when you solved the second derivative equal to 0, and do your sign charts, plugging them into the second derivative, because that's what we want to know, what changes sign. If you have the second derivative equals 0, but I'm just looking at what this says. So in the figure to the right, f prime equals 0 at these inflection points. You're right. So we are going to, so you'll notice on the graph where we had our inflection points. There we go. That's not a max or min. It's kind of like a lull in your graph. Your graph can be completely increasing or completely decreasing. Okay. All right, so let's do some examples. We're going to do a few different functions. And then on your student practice, I've got a bunch of questions that also might mix increasing and notation and things like that together. So number 1, it says determine the intervals. And remember, this is interval notation where our function is concave up, concave down at any inflection points, okay? And we're just going to do the x values again for inflection points because finding the y value is just plugging into the original, and that just takes time. So first we're going to find our derivative. So I get 3x squared minus 6x, and then we're going to set our second derivative. Notice I don't solve my first derivative or even find critical points at all if this is the only thing that I want. So we get 6x minus 6. Okay, so I call this my possible points of inflection. So I'm going to take my second derivative and set it equal to 0. We'll solve this. All right, so that's my possible point of inflection. So then I'm going to label my sign chart because typically you would, you might have the first derivative sign chart and the second. And then we're going to go ahead and just put 1 in the middle. So I'm going to pick 0 and I'll just pick 2. And we're plugging it in to the second derivative. So I get, if I plug in 0, I get negative 6. So that's negative. And if I plug in 2, I get 12 minus 6. Well, that's positive. So what that means is we are concave down and concave up. And since we change signs, I do have a point of inflection. So my point of inflection is at 1. If I had to find the y value, remember you're plugging it into the original. So 1 plus 3 is 4. 4 minus 3 is 1. It's just a coincidence they are the same. We are going to say concave up. We're going from negative infinity to 1. And oops, I meant to say down. Well, I can fix that. So concave down. Okay, and now concave up. We're going to go from 1 to infinity. Once again, the AP and myself, we don't distinguish between if you use a bracket or not, but it makes more sense to me to use a parenthesis because I'm really not having any curvature at 1 since my second derivative is equal to 0 there. So we don't know this because we didn't find our max and min, but it actually occurred between the max and min on this polynomial. And that's where the curve would have been the steepest. So the stationary inflection point, I would have to find my first derivative and plug that in. But I didn't ask for that. And that's not a question that the AP asks or my quizzes will ever ask either, just so you know. All right, so example number 2, I thought I'd find a rational function, determine where the intervals are concave up and down and inflection. So just as a review, if you don't have a variable in the numerator, remember you don't have to do a quotient rule. It's an option. So I'm going to bring this up with a negative exponent. That way I can do a chain rule. Since I have to do 2 derivatives, you want to make this as nice as possible. So we're going to multiply. The inside stays the same. And we subtract 1. And then you always do the derivative of the inside, which is 2x. So if you write this nicer, I actually get negative 8x divided by x squared plus 3 squared. Now, this time, because I do have a variable in the numerator, we will have to do a quotient rule. So I get f double prime. We get low. Sorry, I'm using another tablet, so it's not as nice as my other one. D high minus high. And then D low is a chain. So 2, the inside stays the same. Subtract 1 times the derivative of the inside. All over low squared. I'm going to run out of room, but that's okay. Now, we're going to clean this up. 2 negatives make a positive. If I was solving, I know that x squared, I'll do it up here, plus 3. If we set that equal to 0, because I want to see if it's undefined, that would go on our sign chart as well. I'll get x squared equals negative 3, and when I take the square root, it's an imaginary. We still don't solve. So since I don't have any values that make my denominator imaginary, we can go ahead and set the numerator equal to 0 to find our possible points of inflection. Okay, so I'm going to distribute negative 8x. Oh, that's squared. I can't do that. Trying to erase. Sorry, this tablet is not as good as my last one. Okay, well, yeah. What I notice is they both have, if I look at these two terms, I don't really want to multiply that out, to be honest. So because I'm solving, I can just factor it out. So ignore that negative. I just can't erase it. I tried. I'm going to factor out an x squared plus 3, just one of them. I'm also going to factor out an 8. And that's it. So we would be left with one of those and a negative. So negative x squared minus 3. And then that 8 is gone. That is all gone. So I'm left with plus x times 2 times 2x. So 4x squared equals 0. So I get 8 equals 0, which is nothing. X squared plus 3 equals 0, which is imaginary. We just did. And so then I'm going to combine this. So I get 3x squared minus 3 equals 0. Add 3, divide by 3, and take the square root. So I get 1 and negative 1. Okay, I have a little bit of room here. So we're going to put a negative 1 and a positive 1. This is on our second derivative. I want to use this original one. Since the denominator is always squared, it's going to be positive. And then I just want to plug in 1, 2, 3 numbers. So I'm going to plug in negative 3. So I'm going to use this factored form up here. So I'd have a positive times another positive, and then all of this is that. So I would have, if I plugged in negative 3, I square that and I get another positive. If I plug in 0, well, I still have a positive. I have a positive. Then if I plug in 0, I get negative. And then if I plug in, let's say 2, positive, a positive, and then let's see, 2 squared is 4, 4 times 3 is 12, 12 minus 3 is also positive. All right, so to kind of sum this up, I would have a point of inflection at negative 1 and positive 1 because we did change signs on our second derivative. We are concave up from negative infinity to negative 1. That's a negative. And 1 to infinity. And we are concave down. I know this is really messy. I should have made a bigger box. From negative 1 to positive 1. All right, that was a lot of good review math and calculus. I thought I would do one with E and a product rule. Okay, just to review. So if you don't need to see this, you can go ahead and skip forward. But for solving e, there's some implications. So to do my first derivative would be a product rule. So 1, the derivative e to the u is e to the u, and then the derivative of the exponent, 1 d2 plus 2, and then d1. Now, whenever you do a product rule, one of your strategies is to do a common factor. I don't have to, but I'm going to have to do a double product rule anyway when I go to do the second derivative. So we might as well just factor it out, so it kind of makes our product rule a little easier. So we're going to factor out the e to the negative x, and I'm going to factor out an x. Actually, I'm not. Just going to leave that alone. So we'll leave that as negative x squared. It's really a choice. But if I factored out an x, then I'd have to do kind of a weird product rule, and I don't want to because we don't have that rule actually. So I would be left with negative x squared plus 2x. So now this will be 1 and this will be 2 when we go to do a derivative. If I kept it like this, I'd have to do a product rule here and then another product rule there. So I'm just choosing not to, okay? So our second derivative would be 1 d2 plus 2 and then d1, which is e to the exponent times the derivative of the exponent, which really just makes this a minus. But all right, so now because I know I want to solve this, we do want to factor out the common terms. So notice all of this is one term and all of this is a second term, okay? So we do want to take that e to the negative x out. We want to factor that out. So I would be left with negative 2x plus 2, and then this is really a negative, which is going to change those signs. I'm going to distribute at the same time. All right. I know, I write too big with this other tablet. So we get e to the negative x, and then x squared minus 4x, and then plus 2, which does not factor, okay? So when we set these equal to 0, well, if I have e, I'm going to do it over here. E to the negative x equals 0. Remember, a negative means it's a reciprocal. So this is saying 1 over e to what power gives me 0. Well, really, there's no way for me, e to no power gives me 0. Even if I had 0 in the denominator, that doesn't give me 0, that gives me undefined. The only way to get 0 would be if 0 is in the numerator, and it's not. So what that means is that this is not giving me any solutions. There's no possible points of inflection from that, okay? So we want to solve this. Well, since it doesn't factor, you have to do the quadratic formula. So we get x equals the opposite of b plus or minus b squared minus 4 times a times c all over 2 times a. So that gives you 4 plus or minus, well, 16 minus 8 is root 8 all over 2. And root 8 simplifies. You want to break it down, look for doubles. It's 4 plus or minus 2 root 2 all over 2. And then we divide all three numbers to reduce. So they both divide by 2. So I get 2 plus root 2 and 2 minus root 2. So remember, root 2 is about 1.7, okay? So when we go to make our sign chart, I'm going to just do it here. We've got 2 minus root 2 and 2 plus root 2. I know you never thought you'd see that quadratic formula again, huh? It's rare. I'll be honest, it doesn't show up very often in a calc class. So we want to test. Well, if you're not sure, let's say you didn't even know what root 2 was, pick something that's huge. Pick like -10. And then if you're not sure what's between these, although I've said 2 minus 1.7 is about 0.3, and 2 plus that. So either way, even if I subtracted or I added, that means that 2 is going to be in the middle. So pick 2, and then pick something huge. Okay? So if you're not sure if like, oh, will 0 work? Don't use 0. We are going to plug it in to this form right here. So the good thing about e is that if it's positive e, it's always going to be positive. So e to a negative just makes it a reciprocal. It doesn't make it the opposite sign. So this really doesn't have any effect on our answer. We did need to consider it just in case though. So if I plug in -10, I get 100 minus 40, which is 60 plus 2, we get positive. Plug in 2, 4 plus 2 is 6, 6 minus 8 is negative, and plug in 10, 100 minus 40, and there you go. So we have our points of inflection, and we have our intervals, concave up, concave down. All right, so I'll write them just to clear this out. So points of inflection are x equals 2 plus or minus root 2. We've got concave up from -infinity to 2 minus root 2, and from 2 plus root 2 to infinity. And then we have concave down from 2 minus root 2 to 2 plus root 2. Okay, not pretty answers. But an AP only asks you for one of these things, okay? So I'm doing them all because you just never know what you're going to be asked. The last thing I want to review is trig, okay? So I'm going to go ahead and get rid of all these. Let's delete so I have room. I know. All right, so same thing, concavity. So you did this for the first derivative, this exact function. So if it looks familiar, that's why. The derivative of sine is cosine. The derivative of cosine is negative sine, so negative times negative is positive. We want the second derivative though, and we're going to solve this probably pretty similar. So if you remember, this was from increasing, decreasing. I'm going to go over the same trig review. So the derivative is cosine is negative sine. The derivative of sine is cosine. Okay. So we want to set this equal to 0. So I'm going to add sine to the other side. So what we want to do is we want to know where does the sine and where equal the cosine. So, and we're only on 0 to 2 pi. So I'm going to go ahead and we got 2 pi and 0. And this is going to be our second derivative sine chart. So we need our little review. On the special triangles, if I want them to be the same, well, we want sine and cosine to be the same. So I'm looking at 45, 45, 1, 1, root 2. So you had to realize that you were looking at a 45-degree angle. So the sine is 1 over root 2, and the cosine is 1 over root 2. So that's the reference angle that we want to use, okay? Now I need to find out what quadrant that is. So all students take calculus. And remember, this tells you where they're positive. So we want them to be either both positive or both negative. So let's look at where they're both positive. Well, that's in the first quadrant. So that's going to be at 45 degrees, which remember, 45 degrees, if you want to convert that, 45 goes into 184 times. So we're looking at pi over 4, which is 45 degrees. The other place, sine is positive, but cosine is negative. Cosine is positive, but sine is negative. And in the tangent, since you go to the left, cosine is x, so cosine is negative. And since you go down, that's why sine is negative. So it's also the same in the third quadrant. The 45 degrees always goes in the corner, And so you're looking at this real angle. So you've got 180 plus 45. So that's 225 degrees, which that's 1 pi plus another fourth is 5/4 pi, which is 225 degrees. Okay. I know that was a lot of review. Hopefully you followed that a little bit better since you saw it on the increasing and decreasing. Not the same solving though, okay? We don't have the same answers. So what we want to do is we want to plug in 1, 2, 3 angles into this equation. I'm going to pick the only angle that I really would be able to know, or if I look at their waves, okay? So let's kind of get that idea. Let's say you didn't remember the triangles. I'll kind of describe another strategy. So I'm going to do sine is here. So that's 90. And then let's do cosine. So cosine here, and then I go here. Okay, and then here, and then back up. Okay, so if we're looking at 45 degrees, I'm kind of looking like I want 30 degrees. So this was 45. That's where they're equal. So I'm looking at 30. So I'm looking about right here. So remember, this is cosine, and this is sine. So we just want to know, is the opposite of sine, or is cosine minus sine positive or negative? So cosine is bigger, and if I take off sine right there, I know it's going to be smaller. So that's going to be positive. So I'm going to go up here, and we're going to write positive. Okay. Then I'm going to pick an angle that's in the middle. Well, 1/4 and 5/4, which is 1.25, just pick 1 pi, because we know those exact values. So we're looking at cosine. So, oops. So the cosine at pi is right here. So the cosine of pi is -1. And then we've got minus the sine is 0. So that's negative. Okay. And then this one, well, we have 1 pi. And then what about 1.5 pi? 3/2 pi. Or 270 degrees. That's on our wave too. So use that, which is right here. So cosine, which is green, 0, minus sine, which is -1. So that's positive. Okay, so you don't always have to use triangles to find these sign charts. It really depends on your solving. So we've got points of inflection at pi/4 and 5pi/4. Concave up from 0 to pi/4 and 5pi/4 to 2 pi. And then concave down from pi/4 to 5pi/4. Okay? All right, email me if you need any trig review.